Hello, my name is Robert Smith, and I'm with New River Community College, and today we are looking at assigning the oxidative state to a central metal atom on a coordination compound. So a coordination compound generally is composed of a metal ion that is complexed with what are called ligands, and we have a series of different types of ligands that it could complex with, but the overall charge on the metal atom does not change. So it also ends up based on, unless the ligands themselves are charged. So what will end up happening is that the coordination compound itself may or may not have a charge, and if it does have a charge, positive or negative, it will complex with a complementary ion. So what we're going to do is take this species and break it up. We have 3 potassiums, and we know that potassium has a +1 charge on it. And this gives us a total of +3 from the cation. And the coordination compound is therefore our anion. And it has to have a -3 charge. And the reason why is because the overall complex is neutral. So with 3 potassiums at +1 apiece, you have to have a -3 overall for our iron and 6 cyanides. Now we can take this and split it up. There are 6 cyanides, and each cyanide is a complex anion, and they have a -1 charge. And you learned this back in the first semester of Gen Chem. So you may want to go back and familiarize yourself with some of the complex anions. And so the overall charge being -3, 6 negative charges are assigned due to the cyanide, which means that our iron has to have a +3 charge, because 3 minus 6 is going to give us -3. And that's what we're looking for our charge. So the oxidative state on iron is 3, because the oxidative state has to equal the charge on the species. Okay, let's do another one. So for this one, we have 3 chlorides, and we know that chlorides all have a -1 charge. So that means that our coordination compound is the cation in this case. And it's kind of indicated by the fact that it's written before the chlorides. So this coordination compound has to have a +3 charge. And we again want to split up the stuff inside of the species inside the brackets. So there's 6 ammonias and 1 cobalt. But ammonia doesn't have a charge. It doesn't lend any imbalance of charge to the coordination compound. So that means that the cobalt contributes entirely to the overall charge on the coordination compound. So this would be cobalt 3+. So the oxidation number or oxidative state would be 3. This next one is a neutral coordination compound. So we can just split it up directly. There's 4 carbon monoxides and a nickel. Now, carbon monoxide does not lend to a charge to anything. It's a neutral species. So the nickel is also neutral. And so the oxidation number on nickel would be 0. And one last example. We can take this one and split it up. Let's start with the stuff outside the brackets. So SO4. And again, you want to know that this is a complex anion with a -2 charge. So that means that our overall charge to balance it has to be a +2 for the stuff inside the brackets. And again, we want to split that up. So we have 6 waters and manganese. Because water is neutral, it doesn't lend a charge. The manganese, it gives a +2. So this would have an oxidation state or an oxidation number of 2. The only thing to reconcile is that all of these resulted in a neutral species, overall neutral species. If for whatever reason there's a charged species, so for example, if we went up here and there was only 2 chlorides and this was had an overall charge on this one had an overall charge of +1, you would want to account for that when you're doing your charges. So make sure your charges are balanced to the overall charge on the species. All of these were neutral, so we just balanced them directly. But if there was a charge on the whole species, the whole compound, then you'd want to assign based on that.